Welcome back to the deep dive. Today, we're getting into the real nitty-gritty physics behind a huge industry, hydraulic fracturing, fracking. It's a super technical field, and we've got a study here that tackles a really big challenge, figuring out how multiple fractures interact when they're kicked off close together in these tight rock formations. So our mission today, give you the shortcut, basically, to the latest in how they model this stuff. We're digging into results from something called 3D GXM. That's generalized extended finite element method. If you work in this area, getting that fracture shape right is, well, everything. We want to see what this advanced tool tells us about making fracking predictable, efficient, and, less costly.
Exactly, and that efficiency piece is huge. The sources we looked at, they point out this pretty startling stat. The fracture treatment itself, that can be up to half the total cost of drilling and completing a well in unconventional oil and gas. So if you get that treatment wrong, if the fractures don't go where you want or they interfere badly, well, that's potentially half your well cost down the drain. And that's not even mentioning the risks, right? Like unwanted fractures potentially getting near groundwater zones. So the whole point of the sophisticated modeling is really to get the most oil or gas out safely and minimize that operational risk.
It really sounds like you need, surgical precision, not just like brute force pumping. And the complexity, it's kind of mind-blowing because you're not just simulating a rock cracking open, are you?
No.
I read somewhere it's governed by, 5 different physical things all happening at once, tightly coupled.
That's exactly right. It's what we call a coupled hydromechanical framework. You really can't pull these 5 things apart. You've got the hydraulic fluid flowing inside the crack itself. That's 1. Then there's the fluid flow within the rock pours around the fracture. 2. Then the rock itself deforming, stretching, and opening up. 3. Number 4 is fluid leak off, how much fluid seeps out from the fracture into the rock. And finally, 5. The crack actually growing, propagating. Any decent model has to simulate all 5 of those interacting simultaneously in real time.
Okay, wow. So let's talk about the tool then. If the old methods, the conventional ways, can't really handle all 5 things in these complex 3D crack paths that aren't just straight lines, what makes this GXM thing, the generalized extended finite element method, the big step forward?
Well, it really comes down to flexibility, particularly with the geometry.
Yeah.
See, with traditional finite element methods, if your simulated fracture starts to curve or branch off, you basically have to stop and completely rebuild your computational mesh, all those little calculation points to make sure the mesh lines perfectly follow that new complex crack shape. And doing that constantly in 3D for multiple interacting fractures is just computationally way too expensive.
Sure.
It grinds the simulation to a halt.
Oh, yeah.
GXFM same gets around that. It lets the model represent these complex nonplanar crack shapes without needing the background mesh to perfectly conform to every twist and turn. You can sort of have independent descriptions for the main rock body and the fracture surfaces themselves. Think of it like simulating airflow through a spreading crack in a window pane. With GXFM, you don't have to rebuild the whole window mesh grid every time the crack moves a tiny bit. That freedom is what lets them tackle these big, complex simulations much more efficiently.
Right, that makes a lot of sense. It lets you focus on the actual physics instead of constantly rebuilding the digital framework. So speaking of the physics, what were they assuming about the rock itself? Because, different rocks break in different ways.
Good question. They focused specifically on tight shale reservoirs for this study, and they used what's called linear elastic fracture mechanics based on the Irwin criterion. It's a pretty standard approach. It essentially assumes the rock behaves predictably, elastically, under stress, like a stiff spring. And they justify this because the actual zone where the rock is breaking the fracture process zone is really tiny compared to the huge volume of rock around it. So the bulk of the formation acts like a big, predictable elastic block, and you're just modeling these sharp little cracks forming inside it.
Gotcha. So predictable rock, a flexible simulation tool. They have the GXM, the elastic model, the 5 equations. And then the study ran, 23 different scenarios, basically tweaking 4 main things.
Yeah.
How close the fractures are, how thick the injection fluid is, how many fractures are in a group, and the stress in the surrounding rock.
That's it. Fracture spacing, fluid viscosity, number of clusters, and the remote stress conditions. They really put those 4 through their paces.
Okay, this is where it gets really interesting, looking at the actual results. Let's take that first scenario they looked at. It's a pretty simple setup, right? Just 2 misaligned fractures, one flat horizontal and the other one tilted, inclined at 30 degrees. And the big variable here was the fluid viscosity. Why does how thick or thin the fluid is make such a difference to where the cracks go?
Yeah, it's fascinating how much the fluid properties mediate the stress fields right at the tips of those growing fractures. They ran two main comparisons, keeping the background stress the same isotropic. One case used really low viscosity fluid, 1 centipoise or 1 cp, think water thin. The other used high viscosity, 100 cp. That's quite a bit thicker, maybe like a very light oil.
Okay.
So with the low viscosity, the 1 cp fluid, the simulation clearly showed what's called a stress shadowing effect. It's kind of like, imagine two strong magnets with the same poles facing each other. They push apart, right? As that bottom horizontal fracture opens up, it creates this zone of compressive stress around it. And that stress zone physically pushes the inclined fracture away. So the inclined fracture actively avoids that stress zone. It tends to propagate more towards its outer edge, away from the horizontal one. And the result is they both stay relatively separate, relatively flat. They don't really interact strongly.
Huh. So thin fluid means they kind of repel each other. They compete for space but stay apart.
Mm-hmm.
So what happened with the thick stuff, the 100 cp fluid? Did that thickness just overpower the stress shadow?
It significantly reduced its effect, yeah. When the fluid's much more viscous, it's much better at transmitting pressure evenly all the way to the fracture tip and across the crack faces.
Why?
And what they saw was the top inclined fracture showed, well, significant turning. It started bending towards the bottom horizontal one. It was actively trying to cross into the other fracture's territory, potentially merging with it.
Wow, okay. So the take-on isn't just they avoid each other. It's that the fluid you choose to pump basically dictates whether they'll avoid or try to merge. You can almost engineer that interaction just by changing the fluid thickness.
Precisely. It's like if low viscosity is like trying to get two parallel streams to avoid each other's currents, high viscosity is like forcing them together through a narrow channel until they have to combine, even if they started off angled away from each other. And that choice, that engineering decision, it has immediate cost implications.
Okay, let's talk about those costs.
Yeah.
You mentioned earlier, half the well cost can be in the treatment. So what numbers change between the thin fluid and the thick fluid simulations? What metrics?
Well, look at the pressure needed just to get the fracture started, the breakdown pressure. It was way higher for the high viscosity fluid. The 100 cp case needed about 11 megapascals, 11 MPa, to break the rock. The low viscosity 1 cp case, only around 7 MPa.
That's a huge difference, nearly 60% more pressure just to kick things off.
Exactly. That translates directly to horsepower needed at the surface, fuel costs, equipment wear and tear. Big operational difference.
Okay, pressure is one thing. What are the actual shape, the geometry?
The geometry was different too. The high viscosity fluid resulted in a significantly wider opening near the injection point, what we call the fracture aperture. So if your main goal is to create a really wide open channel for the oil or gas to flow back easily, a large aperture, then you might need that thicker fluid, even though it takes more pressure and costs more initially.
Right, so there's a trade-off there between the initial cost and the potential flow later on.
Always. It always comes back to the design priorities.
Okay, let's move from that simple two-fracture case to something closer to what they actually do in the field, these fracture clusters. The study modeled 3 parallel fractures, all symmetric, like you'd see in a multi-stage job. And here they played with 2 main things: spacing 5 meters apart versus 10 meters apart, and the background stress, isotropic versus anisotropic. Did adding that third fracture make those interaction forces even more complicated?
Oh, absolutely. They definitely amplified. Let's start with the tight spacing, the 5-meter cluster, under just simple isotropic stress first. The geometry immediately got complex. The middle fracture, it grew in what's called pure mode I, which for anyone not deep in mechanics just means it's opening straight apart, purely due to tension pulling it open, like you said, taffy.
Okay.
But the 2 fractures on the sides, the lateral ones, they propagated in mixed mode. That means they weren't just opening, they were also experiencing shearing forces, twisting forces. They actually started deflecting outwards, away from the center one, because of the complex push-pull forces from that middle fracture's stress shadow.
And that viscosity effect we just talked about, thin fluid versus thick fluid, was that difference even bigger here with 3 fractures?
Yes, it was. And this is a really key finding from the study. The difference in how fast the fractures grew, the propagation speed between the low viscosity, they use 0.1 cp here, and the high viscosity, 100 cp, was much more pronounced in this 3-fracture, 5-meter setup compared to the 2-fracture case. So having more fractures close together seems to magnify the impact of the fluid choice. And again, lower viscosity meant faster growth.
Faster growth.
Hmm.
And what about the pressures within the fractures?
That was also really revealing,
Wow.
especially for the high viscosity cases at that tight 5-meter spacing. The difference in pressure between the middle fracture and the outer lateral fractures actually grew over time during the simulation.
Grew over time, so it got worse.
Yeah, it became more unbalanced. That strongly suggests the stress shadowing and the interaction forces weren't just static, they were evolving, becoming stronger and more asymmetric as the fractures got longer. That's pretty much the definition of unpredictable behavior, which is exactly what operators want to avoid, high risk.
Okay, so 5 meters gives you this dynamic, growing imbalance, higher pressures. What happened when they simulated doubling the spacing to 10 meters? Did things calm down?
It was like night and day, seriously. Increasing the spacing to 10 meters visibly dramatically weakened all those interactions. Geometrically, you remember that sort of narrow, pinched necking region they saw between fractures at 5 meters where they were fighting for space?
Yeah.
That largely disappeared at 10 meters. The fracture shapes looked much more uniform, much more, well, predictable.
And the pressures, did they even out too?
Completely. Looking at the pressure graphs for the 10-meter spacing, everything was far more consistent. The lower viscosity fluids still resulted in lower overall pressure naturally. But critically, that pressure difference between the middle and the side fractures, it stayed consistently small throughout the entire simulation time.
So uniformity, predictable pumping needs, safer operations, you'd think.
Exactly. That's the implication.
So this brings up the obvious question. If 10 meters makes everything smoother, more predictable, uses less pressure, is it just flat out better than 5 liters?
Yeah.
Or is there still a catch?
Well, it's that classic engineering trade-off again, isn't it? The wider 10-meter spacing clearly gives you predictability, lower injection pressures, smoother fracture openings. Operationally, that sounds fantastic for managing costs and risks.
Right.
However, if your primary goal is to contact as much of the reservoir rock as possible to maximize drainage area, which often implies needing fractures closer together, maybe 5 meters, is still the target. If you decide you can handle the higher pressures, the higher risk of uneven growth, maybe that tighter spacing is still necessary for your specific reservoir goal.
So the synthesis is really, there's no single best answer. It totally depends on what you're trying to achieve, maximizing the opening, minimizing pressure, maybe maximizing how fast you create the fractures.
Precisely. You have to explicitly model these interactions for your conditions. Otherwise, you're essentially just guessing, and guessing is expensive and risky.
Makes sense. Okay, so beyond optimizing these clusters, these man-made fracture patterns, they also tested the XFEM model on something nature creates, right?
Right.
These simulated naturally occurring fracture patterns, specifically these on-echelon arrays. Those are the stepped offset cracks you sometimes see in rock outcrops. How did the model do with those?
It did exceptionally well, actually. And importantly, the results lined up really well with observations people have made in the field, especially in formations like sandstone. The simulation showed that as these stepped, initially separate cracks start to grow and their tips begin to overlap spatially, the local stresses right around the crack tips themselves actually start to dominate over the larger scale background stress field, the remote stresses.
Okay, the local effects take over.
Exactly. And this causes what's called a mode mixity effect. It basically forces the cracks to start curving inwards towards each other, eventually leading them to link up or merge. The fact that the GXM could capture that specific behavior where the growing fractures themselves dictate the path over the background forces, that really validates its power for looking at complex, naturally fractured rocks, not just nice, clean, engineered scenarios.
That's pretty impressive.
Yeah, and they also noted that even when the interaction was weak initially, like when the on-echelon fractures hadn't overlapped yet, the viscosity of the fluid still had a noticeable impact on the fracture opening, the aperture history. So viscosity matters, even when the paths aren't dramatically changed yet. It just underlines how robust the tool seems to be across different geological setups.
Wow. Okay, that was a ton of information pulled from some really complex modeling work. Let's try and boil it down for everyone listening. 3 core takeaways from this deep dive. First, it seems really clear. The fluid you pump, specifically its viscosity, fundamentally steers the ship in terms of fracture geometry. Thin fluid encourages avoidance due to stress shadowing. Thick fluid tends to overcome that and pushes fractures to curve and potentially cross paths. That's huge.
Absolutely. Key takeaway number 1.
Second, spacing in clusters is critical for both the economics and the predictability. Going from 5 meters to 10 meters apart just dramatically eased the pressure requirements and smoothed out those unstable asymmetric interaction forces they saw in the tight setup. Big deal for cost control.
Definitely. Spacing dictates the interaction strength.
And third, the model really hammered home that external factors matter a lot. things like anisotropic stress, different stress levels in different directions, or just complex existing geology force fractures to find the path of least resistance. And you really need these sophisticated tools like GXFEM to have any hope of predicting what that path and the resulting geometry will actually look like.
Well summarized, those are the big three. And maybe we can leave you, the listener, with one final thought to chew on, something that builds on this but wasn't the main focus. This study looked mostly at that early phase, the initial propagation. We saw how things like the angle between fractures and the fluid viscosity affect the tendency for them to merge or coalesce. But what happens operationally, think about the pumping pressure needed, the final fracture width during the later stages, after that merging finally happens. When two fractures suddenly become one big, complex, irregular shape, the whole dynamic of the system changes completely at that point. And modeling that transition accurately, well, that remains a really significant challenge for the next generation of these simulations, something to think about.